Welcome to the CFE Media and Technology Education Session, Electrical Systems and Rooms. I'm your moderator, Amara Rozgis with CFE Media and Technology. Let's get some basics out of the way before we dive into this topic. In keeping with RCEP policy, please take some time to read the quality assurance slide. This session is designated for technicians and engineers who want to understand the fundamentals and some best practices when designing electrical systems and rooms. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the resources option on the left side of your screen. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. For a seamless online experience, here are some tips. The question and answer session with these industry experts starts in about 45 minutes at 10:45 a.m. Central, 11:45 a.m. Eastern, or immediately after the presentation ends. Answers will be archived with this session. You can see the Q&A details in the Meetings tab on the left side of the screen. Zoom invite details can be found in the Additional Resources tab under the Q&A session. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. Anything with an underline in the text is a link to an additional resource. If you'd like to take notes within this session, please click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Here's a list of the learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. Now let's hear about today's subject matter experts. Brian Renner has 30 years of experience as a manager, director, and engineering leader in the design of numerous types of facilities and has a passion for mission-critical and science and technology facilities. He's a member of IEEE and has served in various leadership roles in the Chicago chapter. He's a longtime member of the Consulting Specifying Engineer Editorial Advisory Board and has been contributing articles and presentations for the brand for more than 25 years. James Lessard is a licensed electrical engineer with 14 years of experience providing engineering consultant services to both public and private sector clients. He has extensive experience preparing lighting, power, communications, fire alarm, systems, and security improvements for a variety of project types and clients throughout the United States. These include healthcare, higher education, government, industrial, K-12, and transportation and infrastructure, among others. Lessard is well-versed in the pursuit of energy efficiency and sustainability initiatives and the pursuit of LEED and similar accreditations. Brian, let's get started.
Thank you, Amara. This is a vast topic with a lot of things we're going to try and cover today. We do have time constraints, as mentioned. The overall session today is 1 hour with presentation and question and answers. We will be using the NFPA National Electrical Code 2020 version, referencing some previous versions as well. This will be using the International Building Code. We're going to be looking at 800 amps and above on primary services. We're not going to get into necessarily electrical closets and smaller spaces. We're not going to talk about hazardous locations, as that is a whole other presentation. And we will be including some good engineering practices which go well beyond the MEC. Next slide, please. Electrical room design is not purely an electrical engineering effort. It has to involve the rest of the design team, architects, structural, mechanicals, and fire protection, all working together to create a room which works well for the building and for our clients. Next.
So in terms of building systems industry, there are a handful of interior electrical spaces that we as electrical engineers and electrical designers need to be concerned with. In particular, we're going to discuss primary service rooms. Every project has a main electrical room where the service enters the building. Electrical rooms that we find on each floor and each area that serve branch level distribution, UPS and battery rooms that often serve IT equipment and other mission critical loads. And then in the case of healthcare, often we find generator rooms where generators are located interior to the building, and computer rooms and utility vaults. There are likely others, depending on the specific needs of a project, but these will be our focus today and are the most common.
So we talked about coordinating with other disciplines. What are some of the topics we're going to cover today that apply to other disciplines? Working versus dedicated space. We're going to talk about dedicated spaces and foreign systems. We're going to talk about fire protection, fire ratings, ventilation, structural, building occupancy, and lighting.
So the NEC requires two distinct and unique spaces be provided around electrical distribution equipment, and they serve two different functions. These are the working space and the dedicated space. And the requirements for both of these are addressed in the NEC, specifically in 110.26. As the name implies, the working space is all about providing for the worker, for the personnel that needs to access the equipment on a regular basis, to provide access and safe working clearance, whether it's for adjustments or to take measurements. It's all about providing space for adds, moves, or changes, etc., that may need to occur about the equipment. While not specifically required in code, one of the things that we do as a best practice in our specifications on a project, we often will require the contractor to physically mark out the working clearances on the floor with either tape or painted lines. And this provides a visual reminder to the occupants of the space that the space is specifically used for access for the equipment and is not to be used for things like storage, etc. Dedicated space, on the other hand, is really about accommodating the equipment and allowing for conduit entry and exit from the equipment, and also for perhaps bus duct or cable tray. Brian is going to talk about dedicated space in greater detail in the later slides. So as we look at working clearance, the width required, the minimum width is 30 inches. But if in the case of equipment that's larger, say we have a 6-foot wide switchboard lineup, the width of the equipment becomes the requirement. So 30 inches is the minimum. If the equipment is larger, so does the working clearance is required to be wider as well. As far as the depth of the equipment, the working clearance for the equipment, it's contingent upon a couple of factors, and this requires references to tables in the NEC. So, when does the National Electrical Code specifically require us to have working clearances for our equipment? Well, in 110.26a, the NEC clearly tells us that equipment operating at 600 volts nominal or less to ground and likely to require examination, adjustment, servicing, or maintenance while energized must have working clearances provided. So the likely culprits here are switchgear and switchboards, motor control centers, panel boards, disconnect switches, circuit breakers, controllers, controls for HVAC equipment, and then oftentimes local jurisdictions have local interpretations to this code, which may require some nuanced working clearance requirements, in this case, transformers. The general rule of thumb that I use is that if the equipment contains overcurrent protective devices, then working clearances are required. But again, check with your local authority having jurisdiction regarding specific local interpretations that may require working clearances for other equipment like transformers. So we talked about the depth of the working clearance being dependent on a couple of factors. It's very much voltage dependent. So if you look at the system voltages, and we can reference back to the tables in the NEC. This gives us an understanding of what the working clearance depth needs to be. It's also contingent upon 3 operational conditions. These conditions speak to how the electrical space is laid out, what is directly across from our equipment. So here's a visual representation of the 3 conditions that we discussed in the previous slide. So condition 1, if we look at the side view, so in this case, a panel board. What is across from the panel board? Condition 1 is an insulated surface, such as drywall, for example, would serve as an insulated surface. Condition 2 is a grounded surface directly across from our equipment on the other side of the working clearance. So that would be concrete or masonry, for example. Condition 3 is electrical equipment directly across from electrical equipment, where you could have the condition of exposed live parts on either side. And so as you can see in the table at the top of the slide, you can see how each condition then implies a different requirement for the depth of the working clearance. So oftentimes, equipment is also required to have rear access, and this is often directed by the equipment manufacturer. What the NEC here tells us is that if the specific equipment requires rear access, this is the minimum working space that you shall provide. In this case, it's 30 inches. So the point really here is that the requirement for rear access is specific to the type of equipment being provided. Switchgear is a good example of distribution equipment that requires both front and rear access. You know, there are other examples like UPSs that often require rear access to get to filters for replacement and so on. There are a number of reasons why we need to provide rear access, and these can be to provide you know, for the handling during removal and installation, but also to provide access for cable terminations and so on. And switchgear, as an example, there are physical barriers between the breakers and the bus, which provide a greater degree of safety and reliability. So we need to provide rear access to be able to get behind that barrier, that physical separation for cable terminations and such. The covers on the back can be either bolted on or doors, depending on the equipment. But the NEC in this case is really just setting the minimum criteria for rear access if the equipment requires it. It's best, however, that we check the manufacturer recommendation or requirements for the equipment and provide the requirements per the manufacturer for the specific equipment.
So let's return a little bit to dedicated spaces, which we touched on, and move beyond working space. Dedicated spaces, again, applies to all switchboards, switchgear, panel boards, motor control centers, shall be located in dedicated spaces and protected from damage. This obviously includes switchboards, switchgear, which was added in 2014, and James talked a little about the differences switchgear have, and we'll talk more about that later in the presentation, panel boards, and motor control centers. So what does this look like? I like to think about dedicated spaces as the no-fly zone. And we get a lot of questions about, as electrical engineers, about mechanical systems being in electrical rooms. Are they allowed, not allowed, where are they allowed? And really dedicated spaces is where you want to focus on in the code. Typical questions come in about, can you have foreign systems such as mechanical ducts or plumbing in your electrical room? Well, it's yes and no. You really do need to understand that dedicated space. You need to understand the height of your equipment. Panel board, switchboard, and switchgear can have vastly different heights. You need to understand where the ceiling in the room is, where the structural ceiling is. The distance is identified as 6 foot or the bottom of structure. understanding that structure is not a drop ceiling. It is the actual structural ceiling in the room. So once you understand that dedicated space and the height, you understand that if you're above the 6 foot or to bottom of structure, you can put mechanical and electrical piping in if protected. Typically you may have, it's not good practice to put piping above that 6 foot above a gear, typically if you're able to have that much space in an electrical room. But you should have some sort of drip pan or protection. You really shouldn't locate it there in general. How above the dedicated space, you can have it in the room. The sprinklers are allowed in the dedicated space. Those are critical to the room. However, again, good practice would be to locate the sprinklers just outside of this dedicated space over the top of equipment.
So we got to make sure that we don't forget about our outside electrical equipment installations. Back in 2014, the NEC added some specific language that requires that electrical equipment be provided with the same basic dedicated equipment and working space for outdoor installations that we would have for the similar electrical installation indoors. The same is true for the dedicated space above and below that equipment. It's important that we take this into account as we coordinate with civil engineers on a project. There's a lot of entities that are vying for real estate on a project, and we got to make sure that we speak up early and often to allocate the spaces we need for our electrical equipment. In the case of an outdoor generator installation, generators, they often have access panels or doors all the way around the entire enclosure to get access to various parts and pieces for mechanical and electrical maintenance and upgrades and so on. So it's important that we coordinate with our manufacturer to make sure that we're not only meeting the working and dedicated space requirements, but that we're also meeting the specific manufacturer requirements for the equipment. So we touched on this a little bit earlier, but I wanted to talk about some of the differences between the primary equipment that we normally see, the types that we see. The primary equipment is often a switchboard or a switchgear lineup where the service comes into the building. Switchboards generally are front access. They can also require rear access depending upon the type, but generally they're front access and they can be placed against the wall. And the overcurrent protected devices in the switchboard lineup are fixed in place. In the case of switchgear, they always require rear access in addition to front access. And the overcurrent protected devices in the lineup are draw-out construction. Basically, they can be pulled out like a drawer for maintenance and serviceability. It's important that our working clearances not only accommodate access, but that we take into consideration in the case of switchgear, the draw-out function of the gear. So as we look at electrical room design, we want to make sure that we're providing proper access. There's a specific case in the NEC where for gear that's over 1200 amps and 6 feet in length, this is large equipment. We need to provide some unique characteristics of the working clearance. Either 2 doors on opposite ends, so one for entrance and one for exit from the working clearance, and the doors need to be 6 feet, 1/2 inch by 24 inches wide. One door can be provided if we allocate double the working clearance that would ordinarily be provided for this gear. So it's either a door on either end, or it's double the working clearance with a single door. Doors must not impede or block the entry or egress out of the working clearance. And the doors must be listed with panic or fire rated hardware on the doors for equipment over 800 amps. And this applies to multiple service disconnects as well.
Okay, let's talk a little bit about beyond the NEC. The NEC is the minimum required that you have to do as a design professional. It's not necessarily the best practice or even the most safe approach to do design, but it is the minimum. So we have a couple of recommendations here when we talk about electrical room design. First, James just touched on the code required minimum dimensions for the doors, but really, when you look at some of the sizes of the switch gear or switchboards, really we recommend 36 inches wide or really double 36-inch wide doors that are 9 feet high. You've got to be able to get this gear or switchboards in and out of the room easily for maintenance and future replacements. The NEC does finally address doors and access doors on equipment with regards to access or egress in a room. But when you're dealing with switchgear, those are draw-out devices. We always like to look at how far those devices can draw out and add that to the overall working space. So if you might need 4 feet and the breakers draw out 24 inches, we just add that to the dimensions. Because really, do you really want to work at 3.5 feet? In many cases, that's the dimension we're using for clearance. But you know, talk to the owner when you're designing the job, talk to the maintenance people, and if you can get more room, it's just better for everybody. On switchgear, you need breaker truck access. We have to consider, of course, arc flash and arc flash zones. The amount of PPE gear is dependent on the amount of arc flash energy, incident energy, and the distance you are away from the gear. This can affect non-technical people who are supervising work. More room, just safer and better. We talked a little bit about structural ceilings and equipment space. Really, the height above switchboards and switchgear in the main electrical room should be considered. The space we would want to normally have minimum is 3 foot above the gear. So look at your gear, your equipment pad, then try and add a minimum of 3 foot above your systems to allow conduits to come in and out. One of the things that's also not commonly looked at, especially if gear is on a lower level or basement levels, is move in and move out paths. Think about how in the future, if a large transformer, a switch gear, a generator, anything that you might have electrically would get in and out of the space in the future. And space planning, work with your architect partner early. We know it's challenging, space is at a premium. Typically they want to build a small electrical room as possible, but your job as a professional electrical engineer is to do early estimates and really try and carve out these primary spaces early with the architect. Next. So let's talk a little bit about fire protection. We get this question a lot. Do you want sprinklers in electric rooms or not? Do you have to? Basically, the NFPA 13 says that sprinklers are required, or you have to have a 2-hour rating. This doesn't mean you can't have both. And there are some local jurisdictions that may want to do something different, but this is a general rule. Yes, you need them, or you need to create a 2-hour rated room. Fire detection is always the way to go with electrical rooms. You want smoke detectors in electrical rooms. In generator rooms, obviously because of the airflow, you can't use smoke detectors, and you want to look at heat or flame detectors in generator rooms.
So Brian touched on this just a little bit in his discussion about fire protection. You know, do all electrical rooms need to be fire rated? Well, no. If the room is sprinklered, we don't necessarily need to rate the room. But there is a specific case in the NEC where we often do run into requirements for fire rating of a particular electrical room. In the case of a 112.5 kVA transformer in an electrical room, if that transformer does not include 155 degrees C or higher insulation interior to the transformer, then that room would need to ordinarily be rated, would be required to be rated. Also, another instance where a rating is required is the emergency systems. This is NEC 700 systems. These need to be protected by a 2-hour rated system. This is specific to high-rise and high occupancy buildings, such as assembly occupancy. And they need to include a fire suppression system. Also, NFPA 110, the standard for emergency and for standby power systems, requires that EPS systems components be installed in separate rooms for level 1 systems. Specifically, a good example of this is a healthcare occupancy that has a level 1 emergency generator system. The EPS piece is the automatic transfer switches. Those need to be in a separate dedicated room for that equipment. And that room must be 2-hour rated. So again, in the case of a healthcare occupancy, as an example, where you often find generators that are interior to a building, the generator room is required to be 3-hour rated. And there's a limitation on the amount of fuel that you can store indoors. And that limit is 660 gallons. But in some jurisdictions, as an example, Chicago, they have a stricter requirement on the limitation of fuel storage in the building. So check your local requirements on that. The other thing to consider too is insurance carrier requirements. Your owner is going to have an insurance carrier, and they are going to have specific requirements as well on a project that we need to be cognizant of.
So let's talk a little bit about coordination with your mechanical or HVAC engineers on ventilation and cooling of electrical rooms. Is it required, and how do you determine the amount of air and or cooling required? First off, understand that the general rating of electrical equipment, that is specifically electronic circuit breakers, is about 104 degrees Fahrenheit. If it gets hotter than that in the room, some of this protective devices can start to have malfunctions or accuracy issues. So that's a kind of the upper limit, but you really don't want necessarily in an electrical room, maintenance electrical room, for it to be 104. You got maintenance people servicing those types of things. We like to recommend that you put that at about 86 degree Fahrenheit average for worst case design day conditions or less. So when you're talking with your mechanical engineer, there's some rules of thumb you can use before you actually go get the actual heat rejection values from your equipment's vendor. So if you've got a room without transformers in it, just gear, panels, those types of things, general rule of thumb to give your mechanical engineers 1 cubic feet per minute per square foot. If you have transformers, you're going to use 1 to 2% of the kVA or 3 CFM per kVA for ventilation. Again, check with your vendors for equipment. The mechanical engineers, if they're experienced, may also have their own guidelines that they've been using. Generator rooms are, again, a whole other topic, but you need to understand the difference between cooling and combustion air. The air going into a generator room there are 2 types. That for cooling, which you normally associate with the radiators, and the amount of air that's used just for combustion for the fuel. Radiators are normally located in the room, but they can be located outside the room. Once you locate them outside the room, you significantly reduce the amount of air, because combustion air is a small fraction of what the total air on a generator is needed. Understand what happens after the generator shuts down and continuing to cool the generator using temperature sensors, and use an average rule of thumb of about 2,500 BTU per hour per kVA rating of generator in the early stages of planning for generator rooms. Later on, you're going to want to bring your vendors in for a sit down between you, the mechanical engineer, and the generator vendor. Battery rooms, UPS rooms. Here's where you want to keep the temperature even lower. There are a lot of different types of battery technology that's been used over the years. Flooded, vented batteries were the old type technology. Most things are sealed or valve regulated type batteries are used. Lithium-ion batteries are gaining ground. Their prices are coming down. But in general, with the sealed batteries, they are very temperature sensitive. Anything above 77 degrees Fahrenheit, their life starts to reduce significantly. So that's the value you want to use with your mechanical engineer to keep that room cool. Lithium-ion batteries don't have that type of temperature limitation, but keep in mind that even if you specify lithium-ion batteries now, the owner may change them to something else in the future if they're on a tight budget. So consider the cooling carefully. Also understand that lithium-ion batteries have different regulations. Fire protection codes are coming out for these types of batteries that are different from the sealed batteries. Safe rule of thumb, 1 CFM per square foot for UPS rooms. And also understand that often a ventilation fan will be needed with concerns about fumes from batteries, even sealed batteries. Local authorities may have issues, and you want to have a fan failure relay to know when the room is not being properly exhausted.
So one element of coordination with electrical that's often overlooked is coordination with structural. If you think about the items that we're putting into a building, the switchgear, the switchboards, the generators, these things have excessive amounts of weight associated with them. I mean, comparable to automobiles or a small truck, for example. The structural integrity of the building needs to be able to support these elements in the space. But in addition to actually physically supporting the load, there's also elements of vibration isolation that must be considered. If you think about a research facility, for example, where you have sensitive equipment in a space, it's important that we consider vibration isolation and the effects that, say, a vibrating transformer or a generator in a building are going to have on the equipment that's adjacent to that space. These are all elements that we need to be coordinating early and often during the design process with our structural engineers. Other pieces that need to be coordinated include electrical rooms, raised floors, and then there's also the miscellaneous pieces that are associated with our installations, like equipment pads and penetrations through structural members, the fire sealing of those penetrations, and also the path of delivery. If you take into account, conduits, oftentimes a conduit rack passing from one end of a building to another end of a building with multiple conduits. It's often overlooked the amount of weight that introduces to the building. We need to make sure that we have that accommodated in the structural design.
Lighting is another key component of electrical room design. The lighting standards generally call for 30-foot candles in electrical rooms, which should be sufficient. However, when you're on emergency power or during an outage, you don't want to just do the typical 1 or less foot candles for egress and emergency access. Basically, good recommended practice is that all the lights in the main electrical room or key electrical room should be on emergency power. It's just simply not that big a cost, even if you don't have a generator to add battery packs. Make sure the entire room is lit. Also switching, you have to have both automatic and non-automatic means. You certainly don't want the room to switch off while someone's working in there.
So I'd like to share an example, a healthcare example, of where we have applied some of these practices on a project. In this particular case, the Franciscan St. Anthony Hospital in Michigan City, Indiana, The building was approximately 500,000 square feet, 5 stories, plus a penthouse on top, a mechanical penthouse on the roof level. The building itself was not classified as a high-rise because the occupied floors were less than 75 feet above grade. This was a developer-led design build delivery project. In terms of electrical distribution in the building, we had 3 1.5 megawatt generators located indoors to the building and 4 main 5,000 amp double-ended switchgear lineups. The campus also has a medium voltage distribution outside the building that fed the interior distribution as well. So in the case of the main electrical rooms, we had the normal main electrical room and the essential system main electrical room. And as NFPA 110 requires, we have separation between those, physical separation. So there's two distinct rooms. The room on the left contains the automatic transfer switch equipment. That's your EPS level 1 equipment that NFPA 110 requires to be separated from your normal service entrance equipment. This represents a very small fraction of the total distribution that was in this building, but it's a good example. You can see the switchboard lineup that we have in the normal distribution that required both front and rear access that are depicted by these hatches in the drawing. Another good practice that we accommodated in this particular building, working with the owner, was providing future flexibility, providing wall space in each of these rooms to accommodate future add moves or changes as needed. Another aspect of the project that I'd like to highlight is the generator room. So this generator room has three 1.5 megawatt generators. You can see we've accommodated, so these generators are fed from buried fuel tanks outdoors. So the only fuel storage that we have interior to the building are the day tanks. So we more than adequately meet the 660 gallon fuel limit interior to the building. And you can see that we've got adequate working clearances around the paralleling gear that's located in the adjacent room with both front and rear access. And then finally, I wanted to look at our typical electrical closets that we had in every area of the building on every floor. In this particular example, we separated out the essential system from the normal distribution. We had them in two separate electrical closets in every area. You can see as these rooms are laid out, we've got adequate working clearances in front of the gear. And in these rooms, you can see that we've got panel boards that are directly across from panel boards. So we had to take into consideration live working parts on both ends, as dictated by NEC 110.26a. And we also considered the rating of the room in the instances where we had transformers over 112.5 kVA. In this particular example, we utilized transformers that included the 155 degrees C insulation, which didn't require any of these rooms to be rated. So this concludes our presentation today. I appreciate everyone's attendance.
Great. Thank you for all of that helpful information. And thank you to these subject matter experts, James Lassard and Brian Renner, for this presentation. Questions will be answered in a live Q&A on October 8th, 2020 at 10:45 a.m. Central, 11:45 a.m. Eastern. Participate in the live Q&A with your Zoom invite details. These details can also be found on the Additional Resources tab on the left side of the screen.